All right, next up we have a talk by Kimo about classifying Mac malware via machine learning. This is also a very interesting topic to me because on Windows we've seen a lot of research gone into classifying Windows malware, but we have not recently seen a lot of that in the Mac OS space. And I'm sure Kimo will talk about some of the challenges, but it is really neat to see that we're gaining finally some parity between Windows and Mac in terms of the Mac research that's coming out. So let's give Kimo a round of applause.
Okay, it's good. All right, thanks, Patrick. I'm excited to be here. As you said, my name is Kimo, and the talk that I have for you today is called Learning How to Machine Learn. And as some background is this, I have had a Mac for quite a long time, and I've been doing security stuff for a pretty long time, but it's only been in the last couple of years that I started to get interested in Mac OS security. And around the same time, I was taking a class in machine learning, so I was trying to figure out how can we use ML to solve security problems. Like Patrick mentioned, I was doing some research and I found quite a bit of published work on this is how you can use ML to classify a PE file as malicious, or how to classify a PE file as packed. So looking around, I didn't see a whole lot of similar research being applied to MachOs and the Mac space. That's kind of how this whole thing got started. And if you all are interested in going on that journey as well, I've put together a GitHub with a Jupyter notebook where I'm explaining how all this stuff works. And it's got some sample data that you can use, and we'll talk about how to use it. So with that, the agenda for today is first downloading some malware samples. So in order to do machine learning, we've got to have data. In order to have data, we need to download some malware, so I'll talk about how I did that. Data pre-processing, once we have MachO files, we need to extract information out of those files so that we can apply some ML against it. In feature selection and engineering, we'll talk about how to transform the data so that it's more applicable to different algorithms, fill in missing values, that kind of stuff. Hyperparameter optimization. Every machine learning algorithm has a set of hyperparameters that are going to control how that model works internally. So we'll look at how to automatically find the best parameters for our particular problem. And then model training, we'll take all that stuff, put it together, make a machine learning model that can do some predictions on whether something is malware or not. And then lastly, we'll look at ways to assess and validate those models with a special emphasis towards visualizing how well it's done. Starting off with the malware sample collection. So my experience going through some machine learning courses was Intro to Machine Learning. Go to Kaggle and download the CSV that has all this information about people who were on the Titanic, and then make a machine learning model to predict whether they would have survived or not. And then go do a machine learning course that's focused on cybersecurity. Here's a data set from NIST with all this information about network traffic in this network, and it's already labeled for you. So in all those cases, the data was provided to me. So when it came time to do my own research, I had to figure out how to go and get my own data. So the processes, the ways that I went about doing that, went to some of the repositories that are online. So the first one is VirusShare. You can email them and they'll hook you up with an account. Once you have access into their repo, you can search through it to find some malware. And the way that they kind of extract information from their files, they essentially run file against all of their samples and store that string inside of their database, and then you can write a regex to search that string for specific file types. So just an example of searching their repo to get MachO files. With VirusTotal, at the time, I was affiliated with the university, so VT gave me access to their academic API. And what that means is I had higher API quota, and they also gave me access to a Google Drive where they have some zip files that they've made with different types of malware. The limitation that I found there is that those zip files were actually empty, or did not have MachOs, a lot of MachOs, specifically in their MachO collection. Now through work, I'm lucky enough to have access to VT Enterprise, and if you are as well, then you can use a query like this to search for MachOs, and specifically for samples that are going to have 3 or more detections from the antivirus engines that VT is running. And then last but not least is Objective-C. So Patrick curates maybe 150 or so malware samples right now. So one-stop shop to get some high quality Mac malware. Now I was doing a supervised machine learning problem, which means that I need both malware samples and benign samples, and then I need to label them as whether they are malware or not. So I need to go and download some benign samples. Some ways that you could do that, you could just use the MachOs that are going to be present on a base install of macOS. But one of the things to consider there is that the stuff that's in like /user/bin kind of follows that Unix philosophy of like a small program that does one thing. So it's not going to generalize out to applications that a user is going to download or the functionality that malware might have. So what I wanted to do was go find some other stuff. So I went to the Mac App Store and Softronic to find more different types of things. As an example, if we're looking at malware and it's a piece of ransomware, it's going to load a library that contains cryptographic functions, and it's going to call those functions to encrypt data. I wanted to find something like a password manager, which will load cryptographic libraries, encrypt things, but for good purposes. And so that way, when we build the models, right, we can discriminate between malicious and benign use of those APIs instead of just the presence of those APIs. So I went to the Mac App Store, went to a website called Softronic. They categorize their applications, so I just downloaded like the first 20 things that showed up in each of those categories. Now I have a bunch of MachO files sitting on a hard drive, but I still need to take information out of those files so that I can do something with it. So as kind of covered before by some other presenters, MachO consists of a header, load commands, and then data. In the header, we're going to find things like flags for how the library should be, or the executable should be loaded. Load commands are going to have things that specify like the minimum macOS version, or here's a dynamic library to load, or here's a section or a segment to load from this library or this file and map it into memory for execution. And then in the data section, we're actually going to have the different segments and sections that compose that file. So you could write your own tool to do that. You could use something like OTool or JTool and parse it. The challenge there is you get text, and I wanted something a little bit more organized. So I found a Python library called MachO Libre, and MachO Libre will parse the executable and then return a JSON object to you. So sweet, exactly what I need. Then I ran into another problem where with machine learning, we have matrices of data, not JSON files of data. So I needed to take the JSON files and then load them up into a pandas data frame. And the pandas library has the ability to read JSON files, but with MachO Libre, it's giving you these kind of like recursive JSON objects. Because, for example, it's going to parse a section, and that section is going to get the size and the name of the section and the entropy of the section and the protections from memory when it gets mapped. And all of that is a sub-key of the segment, and that's a sub-key of the MachO, which is a sub-key of the file. And so it's difficult to parse all that stuff out with pandas. So the approach that I took to solve that was just write my own Python that'll iterate through all the keys and sub-keys, grab each of those objects, and then just make like one big flat JSON file with all that information. So once all that was loaded up into pandas, you could start asking some questions and poking at the data. There are 3 questions that I wanted to be able to answer with this data. So that was 1, is this file malware? 2, is this file packed? And then 3, is this file packed malware? In order to poke at that, we're going to run some essentially equations against it. And just like back in school, we have y equals x plus something. Our y, in this case, is going to be the column from our data that we want to find the answer to. So in my case, I had a column named malware, column named packed, and then one named packed malware. So those are each of my y values. And then we're also going to have x being basically all the other features that we've pulled out of these files. And then inside of the scikit-learn framework, they have a nice little function to split the data between training and testing. And then we're doing that so that we don't like pollute answers with training data. So next was feature selection and engineering. We've got data inside of a data frame. It's all loaded up, it's split off. Now we need to do some more stuff to it. The stuff that we need to do is fill in missing values, scale numbers, and then encode strings. I don't do a whole lot of memes in a lot of my slides, but this one did really speak to me because when I started doing machine learning, it's what I felt like. I was just throwing random stuff at a wall and then getting like an answer and saying, okay, cool, it worked, but I don't know how. And it took a little bit of time to come to terms with it because there was like a voice in the back of my head that was like, hey, you've been doing security for a while, and you're supposed to be like an expert, so shouldn't you just figure out what's the important stuff from all these files to call it malware? But the whole purpose of machine learning is you have all this data, and you just let the computer figure out like what each of those features mean, how they're related, and how they answer the question that we're asking of it. So once I did that, it made a little bit more sense, and I felt less awkward doing it. So filling in missing values. Inside of our big matrix, if our machine learning algorithm encounters like a null or like a not a number type of value, it's going to error out, so we got to fix that. The process that we use to fix that is called imputation. A few different strategies that you can employ there. You can either fill in just a constant value for anything that's missing. If it's a numeric data type, then you can take all of the values inside of that column, do something like average them out, and then fill in missing values with the average. Or if you've used Excel and there's that little black box in the bottom right corner of a cell, and you can like click it and drag it, and then it just populates the last cell down through the next cells, you can take a similar approach as that. In scaling numbers, so some machine learning algorithms are going to want data to be normally distributed, or it'll be sensitive to outliers. So this is just taking numeric information and then normalizing it. And then encoding strings. So ML is using numbers to do math. It can't do math on a string. So if we have a string value, like the name of a dynamic library that gets loaded by a binary, we need to take that and do something with it. We can binarize it or do something called one-hot encoding. That takes all of the values that are in one column and then turns those into individual columns. So if we had a.dylib gets loaded, a.dylib would become its own column, and then we'd fill in 1 or 0 to indicate the presence of that particular library in that particular sample. So once all that's done, we have some features. And when I did this, I had about 2,400 features, so 2,400 columns of data. And not all of that's going to be important. So we want to find only the parts that are important and use that. And then the reason why we want to do this is because this was a pretty limited data set that just used information that you can parse out of a MachO. But it didn't include things like the strings that are present if you ran strings. And it also didn't disassemble files and then use bytecode sequences to say whether this was malicious or not. If you did those things, you might have a lot more columns. And as you add in more data, whether horizontally or vertically, you increase the amount of memory you need, you increase the amount of compute that you need. And again, a lot of it's just not going to be meaningful to answer the questions that we have. So we can use some features from scikit to find the features that are going to be relevant to us. Some ones that I tried are select k-best, which just gives you measures like the information gained from each of the features, and then gives you the k number of those that you asked for. Select from model will instantiate a machine learning model, feed in random features to those models, get the predictions, and then from those most accurate predictions, give you the number of features that gave you those predictions. And then sequential feature selection is kind of similar in that it's going to instantiate a model, and then you're going to either do forward sequential feature selection, where you start from 0 features, and you take the best performing and add it, best performing, add it, until you get the number you ask for, or reverse, where you start from all your features, and then you take away the least performing, until you get down to the number that you wanted. So you pick one or the other based off of how many features you have total and how many features you want to get down to. And then the last thing I tried was principal component analysis, which is not strictly feature engineering, but it does give you a measure of how much that component contributes to the change in the amount of information between them. So you can either ask for n components, so a component is essentially a feature, or you can ask for a float, and if you ask for a float, it will give you the number of features that explain that amount of information within the data set. So as an example, when I used PCA with 0.95, so I asked for 95% of the information explanation, it gave me 250 or so components. So out of 2,400, went down to 250, 10%, that's about 10%, right? So then 10% of the features explained 95% of the information. When we're doing that feature selection and engineering process, we'll want to use something called a pipeline, and that just sequences all of these steps together so that we perform it in a repeatable manner on the data that makes sense. So this is just an example of selecting all of the numeric features and then all of the categorical features, which are like strings and objects. And then for the numerics, we're going to fill in any missing values with just a constant of 0, and then apply a standard scale to all of those columns. And then for the categorical features, filling a constant value of missing, and then performing one-hot encoding to, again, take those individual values and then make new columns out of them. So now let's talk about hyperparameter optimization. All that stuff was having to deal with the data, and then this is having to deal with the model. Every machine learning model, again, is going to have its own set of hyperparameters that you'd want to look for. used a random forest classifier in this research, and a random forest is composed of decision trees. So we see here are a couple of decision trees that are going to make a determination at each node whether it should branch off into a new set of features. And as so the random forest is a bunch of decision trees that get made, and that's our forest of trees. We feed in random features to each of those trees, get predictions from them, and then once they've all made their predictions, we either average it out if it's like a regression problem where we're trying to find a number, or we just vote on like the highest number of classes for a classification problem. And then the output of that is the answer from the model. So the hyperparameters for random forest are what you see on this slide. There's n estimators. That's the number of trees to build for the forest. So in this case, you see 2 trees, so it could have been n estimators was set to 2. Criterion is going to be how we measure how we split at each branch. You can have either a Gini coefficient or an entropy value. Min sample split is going to define how many samples need to be present at a node in order for us to split. So if we had like min sample splits up to 5 and only 4 samples make it down to that node, we don't split further because we haven't met that threshold. I said you're going to get random features assigned to each decision tree, and then max features will define the maximum number of features that can be considered at any given node for splitting. And then lastly is max depth, and that's how tall our decision tree can go, basically how many times it can split or branch off. So hopefully this helps to visualize how these things that you would try to solve for feed into the actual algorithm. In order to search over and find the optimal hyperparameters, we can use a function called grid search CV. So it's going to search a grid, and that grid is like an object or a dictionary of the hyperparameters we want to look for. And then, so if we said our grid is going to be criterion, and we want to search for either Gini or for entropy, and then we're going to have max depth, and we want to do a range from like 4 to 10 maybe. We spell all those out as part of the grid search, and then we do CV, is cross-validation. So this is going to take our training data and do some further splits off into some stuff called folds. So we, by default, do like 5-fold cross-validation. So we take our data, split it off into 5 folds, and then say then fold 1, maybe data set 1 of that is going to be our testing data, and the other 4 are training. And then as we go through each fold, we swap out the testing set with a different one. And that way we can make the model, try out the parameters, get predictions, and then test it against the answers, and then see how it performs. That's how we get those optimal parameters. Once they've been found, you can visualize them in pandas. So as an example here, we can look at the score. And I found, in this particular case, I found 3 particular combinations of hyperparameters and features that would answer a particular question at 100% accuracy. So that's pretty good. Some of the other ones, not as good. Okay, now we'll talk about model training, which is the easy part because we've already done all the stuff that we need to do to build the model and make predictions. So after having got the data through feature selection and engineering, and then having got the optimal hyperparameters through that HPO process, we can either just manually type in like the specific features and the specific combination of hyperparameters. I like to just store them as like dictionaries and then index into them to get the right stuff. Make our pipeline again taking the numeric data and the categorical data, applying those transformations, and then when we call .fit, that's the function that's actually going to train the model. Once that's done, we have a model that can do predictions. So like you see at the bottom, we just call .predict. So in that case, at the end of that, we've got an array of like ones or zeros to indicate whether that sample is predicted to be malware or not. And now we want to see how good it did. So we're going to do some model evaluation. We got a few different ways that we can do this. First is going to be confusion matrix, which will plot like our true positives, true negatives, and false negatives. Precision recall will plot the precision and recall values on a curve, and then we can use that to figure out a threshold for actual like production purposes. Receiver operator characteristic curve is similar. It's going to plot our true positive rate versus our false positive rate. And again, then we can find like where we want to set the threshold for that. And then some numeric values are just the accuracy and then F1 score. And F1 is like a balance between the precision and recall values. So if you want just a single number that tells you like how well your model is doing, you could just go with the F1 score. And an example of what that might look like is here. On the left-hand side, we've got our confusion matrix. And what we want to see is basically a diagonal of high saturation. So that's a kind of visual cue to us that we're getting a high number of predictions in the true positives and true negative columns, and then low predictions in the false positive and false negative columns. In this particular model, you can see that the false negative has a little bit of light blue, so it didn't perform super great. And then in the middle, we've got a precision recall curve. This one just kind of takes a jump off a cliff and goes straight over to the right-hand side there. Normally, this would be a little bit more jagged and would have like individual steps between each of the different thresholds there. And then for the rock curve, again, it kind of just goes up and over to the right, where normally we'd see a bit more of a jagged line. And then accuracy and F1 score, less than 95, so not actually super great on figuring out if a sample was malware or not. But when I ran it against the packed question, got really, really good results on determining if a file was packed. And then just kind of at that intersection, somehow the packed malware predictions actually did pretty good as well. So in this case, it might indicate that we need a different set of features. So again, maybe going back and looking at the strings that are present in the MachO files, maybe doing some disassembly and bytecode sequencing and all that kind of stuff and adding those in as features. Alternatively, you could do some like dynamic runtime analysis and pull some features out of that, like what files does it create or what network connections does it make, and then use those for a separate set of features. So that was kind of end to end of what I learned from starting off with machine learning and then kind of putting it into a practical application. And with just a few minutes left here, I thought I would show you how easy it is to take all that work and then to go deploy it into production into Amazon SageMaker. And ignoring this thing for a second, I do think that SageMaker is a super cool product to make it easy to do a whole bunch of this machine learning stuff. And now that I work there and I get to use it for free, it's even better. But it is really simple to take all of that work and then go deploy it. So a couple things. First, we're going to install SageMaker into this Jupyter notebook. Next, we import joblib, which is going to let me export my model into a single file. I'm going to take the features that I had done the engineering and selection on, export that as a JSON file. The only thing you don't see on this slide is all of that Python that I wrote, that I told you about to kind of take the JSON objects and then make a flat JSON. Just took that, copy and pasted it out into a separate file called script.py. And then you do have to make 4 functions for SageMaker, but it's like 10 lines of code total, so it's pretty easy there. So with the model, with the features, and then with the script.py, we're going to tar all of that up and then upload it into S3. We import SageMaker and then call sklearnModel, pointing it to that tar file that was uploaded into S3. Tell it when you start the container, run the script.py that we've uploaded to S3. And then lastly, just tell it to deploy our model for real-time inference. And so once that completes, you have something that's in the cloud that you can send data to, and then you can get predictions back from. Whoops. And so here's an example of that. I had a separate set of data where I just went through VirusTotal, downloaded some new malware files, ran them through MachO Libre. So read the JSON file, and then just call .predict on my predictor. It sends the JSON up into SageMaker. Within a second, it processes it and then gives a result back, in this case in JSON. And we see that the verdict was malware, which is exactly what I was expecting from this case. So yeah, that's how easy it is to take all of that work that you've already done and then just go upload it to there. So it's really cool. And then, as kind of mentioned by Kristen earlier, what you don't see is all of the time that I spent banging my head against the desk trying to figure out how this stuff works. There's certainly a learning curve to all of the things, and I am by far not smart enough to learn it by myself. So I'd like to give a shout out to the people that you see on this slide for helping me out along the way. And there's many more who didn't make this cut, but they're so cool. And so thank you to them as well, and for you all for being here and listening to me. I guess I have time for questions, if anybody has any. Yes, sir. The question was, do I have the Jupyter notebook up in Google Colab? I don't. I do have it up in GitHub, so you can pull it down, and I run Jupyter either in my home lab or in SageMaker, and then you can run that notebook wherever you'd like to. Yeah, so the question was like, how often do you have to update the model? And like all good security questions, the answer is it depends. So you'd want to evaluate the performance of that model over time, and then determine your criteria for when you'd want to retrain it. So let's say it's going for a month, and then you see like the accuracy scores are starting to dip for whatever reason. That could be an indicator that you'd want to go and retrain it. If you're dealing with like time-based data, you might have some sort of indicator in that time, like seasonality or something like that, that might make you want to like retrain it. So I know it's not super prescriptive, so sorry.
With all the samples that you collected, do you have any funny stories about like the malware that looked like super sketchy, or kind of like right on the edge, but they were just maybe creating very solver and kind of
Yeah, so the question was, did I find like any super sketchy samples while downloading all that malware? Okay, or if it was a benign file, but it just looked kind of sketchy. I didn't, dive deep into each individual sample, so I couldn't say it gave me a feeling. But that's probably reflected in some of those accuracy scores, right? Because the machine learned what it thinks was sketchy based off of what I downloaded. So some of those misclassifications are probably because there were sketchy things in those benign files that just made the computer think that they were malicious.
You mentioned the challenges that of first gathering a sufficient sample size, essentially. Do you think that your models will improve or will need some tweaks, kind of to fall off that question, as you collect more Mac malware? Or do you think that you have a pretty solid baseline and it'll more just be kind of like, it depends, like you said?
Yeah, so it wasn't a huge data set. It was like 1,000 samples of malware and 1,000 benign files. So if you did something like, if you had VT Enterprise and you could download all of their MachOs, having more data is almost always better. And then what I didn't touch on was another way to collect samples, right, is if you're really hardcore, you just go set up a botnet or a honeynet and let people give you samples on the internet, so, or a botnet too, and then whatever. No judgment.
Have you talked to any of the antivirus companies? Because I imagine they have pretty good sample sets. I know they're not always willing to share, but if you're developing this lovely model and this machine learning stuff, maybe they'd be open to collaboration. Have you thought about that or talked to them or tried and failed? Like, what are your thoughts on that?
Yeah, I did not, but that is a good idea.
Let's give Kimo again a round of applause.